Here are solutions to homework set number 9 for ECE 341 random processes. This homework looks at Weibull distributions and the central limit theorem. Now the first problem is, given the circuit where the resistors have a 5% tolerance, find the PDF for Y. Well, one approach is to first do a Monte Carlo simulation. I'm going to pick 10,000 elements, random values for the resistors, calculate Y, and then plot them. So this is the CDF. When I sort the data, what comes out to be the CDF, the probability that the voltage is less than minus 36 volts is basically 0. Probability goes to 1. Probability the voltage is less than minus 24 is 1, with the most likely being right around minus 30 volts. So there's your CDF. Find the PDF. Well, if I differentiate that, that'll be the PDF, but this is kind of hard to differentiate since I don't have the equation for this line. Weibull distribution can curve fit just about anything. So come up with a function. Here what I did is I took the data and I saved it. Let's go into MATLAB. So here's the function that I wrote for the circuit. I calculate the data, then save it. I saved it under this file, homework 9, and the variable is Y. And if I run that, pretty much same as the homework. Where's my graph? That's what the graph looks like. Now, I'm going to create a function in MATLAB. I'm going to load homework 9. That's got my sorted data, Y. That's the voltage that I'm looking at. Here's the probability. Kind of same thing I had before. Given the voltage, here's the probability. Come up with a Weibull distribution that approximates that. So I'm going to pass my guess of k, lambda, and x0. That's my left endpoint. Once I have that, this is the CDF for Weibull distribution, shifted by x0. Plot the two together, calculate the sum squared error. So for example, in MATLAB, I can sit there and say, let's try 111. And here the red line is my Weibull distribution. There's my data. That's basically a really bad guess. The last parameter is my offset. So let's change that to minus 36 volts. That's better. That's at least on the graph. So let's try k of 2, lambda of 2. Okay, maybe k of 5. Getting closer. I can guess again, or let MATLAB guess for me. We use fmin search, minimize this function, and there's my initial guess. And MATLAB will sit there and iterate, guess again. It actually does a really good job. When it's done, it'll kick out and say, that's the best I could do. Here is your k, there's lambda, and there's the offset, x0. And there's the sum squared error. So once you're done, again, it helps to give it a good initial guess. Once you're done, the two curves match pretty well. From that, I know the PDF. So given k and lambda, there's your PDF, there's the CDF. Adding in the offset, so this is how far you are from the left endpoint, x0. There's your distribution, and if I plot that in MATLAB, here's your CDF, there's your PDF. And it kind of makes sense. When the slope is a maximum, the derivative is a maximum, slope goes to 0, PDF goes to 0. That's one use of a Weibull distribution. I can curve fit pretty much anything. And a Weibull distribution is able to curve fit a large number of distributions. It's pretty versatile. And the other advantage is once I know the CDF, I also know the PDF. And there's just a few parameters. So that was problem 1 and 2. Problem 3 and 4 don't exist. I miscounted. Problem 5 is the central limit theorem. Suppose I roll 6 six-sided dice. This is a problem we did before. Using the normal approximation, I determined the mean, the standard deviation, and the probability that I'm going to get some rolls. So if this is for a single six-sided die, the mean and the variance. For 6 dice, the mean scales by the number, by 6. The variance scales by 6. Take the square root to get the standard deviation. And that's kind of an oddity. The standard deviation is what we use, but it's not what's linear. It's the variance that scales. So this is what the PDF looks like for six-sided dice. Mean of 21, standard deviation 4.18. Using the normal distribution, I can start doing things like what's the 90% confidence interval? For normal distribution, 5% tails corresponds to a z-score of 1.64485. So I want to go left and right that many standard deviations, which means that 90% of the time my rolls will be between 14.1 and 27.8. Rounded to integers, of course, since these are dice. The probability of getting more than 29.5 is how far is 29.5 from the mean in terms of standard deviations. That's your z-score. That is 2.03 standard deviations away. Using a standard normal table or StatTrak, I can convert that to a probability. 2.03 corresponds to an area of 2.1%. And if we go back to homework set 4, where we use convolution, actual odds are 1.94% versus 2.1. Basically, it's the same answer. The nice thing about using a normal approximation is with Monte Carlo, I had to roll the dice 100,000 times. For enumeration, it's 6 to the 6 times. Here, I didn't have to roll the dice at all. Problem 6. Suppose I roll 12 six-sided dice. Again, we did that before using enumeration and Monte Carlo. Here, we can do that without rolling the dice at all. I know what the answer is. I know the mean of a single six-sided die, so 12 six-sided dice will have a mean of 42. I know the variance of a single die, so 12 dice will have a variance of 34. Take the square root, standard deviation is 5.9. That's all I need. If I know the mean, the standard deviation, I know what the distribution is. Again, to get the 90% confidence interval, I want to go left and right of the mean by 1.6445 standard deviations. So doing that, I get that I would be between 32 and 51. Same thing we got in homework set 4. If I want to know the probability that I'm more than 49.5, take the distance to 49.5 in terms of standard deviations. That's 1.2 standard deviations, the z-score. Convert that to probability using StatTrak, and I get 11.18%. The actual odds are 10.36. Again, not exact, mainly because I'm converting integers to continuous number. So if I go, here is 49, here's 50. I've got a curve like this. If I take 50 as my point, I'll be too low. If I take 49 as my point, I'll be too high. So where do you put the dividing line? I picked it in the middle, and this isn't quite symmetric, so it's a little bit biased. But pretty close, 11.18, 10.36. That's just a feature of approximating a discrete function with a normal approximation. You're kind of stuck with trying to figure out where do I put the threshold between the two integers. Problem 7. Roll 2 4-sided dice, 3 6-sided dice, 4 8-sided dice. We did that in homework set number 4. Now, just using a normal approximation, I don't have to roll the dice at all. I know what the answer is. The mean scales be twice the mean of a 4-sided die, 3 times 3 6-sided, 4 8-sided. The mean will be 33.5. The variance scales. The variance will be 32.2. Take the square root, 5.67. These two numbers define the normal distribution. With that, again, I can find the 90% confidence interval, take the mean, plus or minus 1.64 standard deviations. I'll get numbers between 24 and 42. 90% of the time. Same thing we got with convolution. The probability of getting 39.5 and higher, again, find out how far is 39.5 from the mean in terms of standard deviations. That's the z-score. Convert that to a probability using a standard normal table, 14.8%. And that's just what we got using convolution, 14.8%. So that is homework set number 9. Again, Weibull distributions, you can curve fit about anything, and they're kind of useful. If I don't know the distribution, a Weibull will curve fit it. And the normal approximation. If I know the mean, I know the standard deviation, I don't have to roll the dice. I know what the result's going to be. It's going to be a normal distribution scaled. The oddity is that the variance scales and the mean scales. It's the variance, not the standard deviation. Homework set number 9 for ECE 341.